Well, hello, welcome again. This is the final recording for Maths 315 on topology and analysis. This is chapter 10 and this is the fourth recording. And we're going to look here at, we've been looking at topology, and we defined last time what we meant by a topological space. Just to quickly recap that, it was a pair of objects. One is a set and one is a collection of subsets, with the following property: the full set had to be part of the collection, the empty set had to be part of the collection of subsets, the union of any number of these subsets in T had to belong to T, and the intersection of a finite number of subsets in T had to belong to T. And we're going to call the elements of this T open sets. No mention or no idea of distance anywhere here. This is purely in terms of set theory. And I did a couple of examples of those. And I want to now try and define what we mean by continuity in a topological space. So we saw that on the real line, if f was continuous, then the inverse image of an open set was also open. And we saw that if it was not continuous, I showed you an example of where the inverse image of an open set was not necessarily open. So we're going to take this now and use this as the basis of our definition of continuity in a topological space. I'm going to define continuity in a topological space by saying, suppose f is a function from the topological space xt to another topological space ys, so that a function between two topological spaces. We say that this function is continuous if and only if the inverse image of any element of S belongs to T. So we take, this is a little bit like what we were doing on the x-axis, this is like we're doing on the y-axis. We take an interval. We took an interval on the y-axis and looked at its pre-image. Now we're going to take any set in S, these are all our open sets, and we're going to say that it's continuous if and only if the pre-image of any of the sets in S belongs to the set T. Now this is quite subtle and quite sophisticated, but you might like to think about this. The point is, we're defining continuity now without any epsilons or deltas and no measure of distance. We're defining it purely in terms of inverse image of a set in one collection of sets in terms of another collection of sets. And this, as I said, I'll do some examples in a second, but this definition enables us to define the concept of continuity without any notion of distance or close to. It is the most primitive concept of continuity in mathematics. Topological spaces, although it looks very abstract, actually have lots of important applications, believe it or not, in mathematics. And topology is a very big area of modern mathematics. So here's an example, and we'll work through this one carefully here. So here are my sets. I've got x as a, b, c, d, and y is the set x, y, z, w. We're going to take a topology on x, which is going to have the following sets in it. It's got to have the empty set. It's got to have the set x. I'm going to put the set containing a in. I'm going to put the set containing ab in. And I'm going to put the set containing a, b, c in. Now just notice it is a topological space. If you take the intersection, say, of these two, then you get a, and there it is. Take the intersection of these two, you get a, but there it is. Take the intersection of these two, you get ab, but there it is. Take the union of these two, you get this one. Take the union of these two, you get this one. Take the union of these two, you get this one. So it's closed under unions and intersections, and it's got the empty set and the main set. Now I do a similar thing here. I'm going to take a topology on this one. Again, it's got to have the whole set. Y has got to be there. The empty set's got to be there. This time I'm going to do a similar thing. I'm just going to take set containing x, set containing y, set containing xy, these two, and the set containing yzw. And again, if you take the intersection of these two is x, intersection of these two is y, intersection of these two is y, intersection of these two is also y, that's there. And if you take unions, union these two, you get this one, union these, this and this one, you get the whole of y back again. Union these two, you get this one, and so on. And union this with this, you get x, y, z, w, which again is back in y. So these are two. This is a topology on x. This is a topology on y. You don't need to prove me that. I'm just showing you what it does. But here we're told that xt and ys are topological spaces. Now I give you a function that's between the two of these topological spaces. And what I do is I'm going to map a to y. B gets mapped to to Z, and D gets mapped to Z, and C gets mapped to W. And we're asked to explain why f is continuous. And so we'll do that here, and then I'll come back and look at showing one that's not continuous. So here are my spaces here. So there's my capital X is X, A, B, C, D, and there's Y is X, Y, Z, W. And we were told that A got mapped to Y, B got mapped to Z, right, D got mapped to Z, and C got mapped to W. Now what I need to do is I need to take the pre-image of all of the elements of the topology for Y. So just remember what the topology is. I need to take the pre-image of all of these sets here and see what they came from under this mapping. So pre-image, I should say, of y is x. So if you look at these and say where did they come from, well, this one came from A, this one came from B or D, this one came from C. So the pre-image of these is A, B, C, D, and that's equal to x. The pre-image of the empty set is the empty set. The pre-image of x, well, it didn't come from anything, so its pre-image is also the empty set. The pre-image of y is just the set containing A. The pre-image of xy, so that's xy, that's just A again. And the pre-image of yzw, that was the last set in S. So yzw is A, B, C, D, and that's just everything. That's just x. And so all of these pre-images, these all belong to T. Remember what T was? T was this set here, and all of these belong to T. And so therefore f is continuous. The pre-image of all of the open sets in S are all elements of T. That is, inverse image of open is open. Now on the other hand, if we look at this function g, same x, t, y and s, this time g of a is g of b is x, g of c is z, and g of d is w. We want to show that g is not continuous. So in this case we're going to do a similar thing. So there's my x, which is a, b, c, d. Now g of a was x, g of b was x, g of c was z, g of d was w. Now if we take the pre-image of all of these, we get a, b, c, d. That's back to x again. Pre-image of 0 is 0. Sorry, if the empty set is empty set. Now pre-image of x is a, b. Well, that one's okay because that one was in T. The pre-image of y, well, y didn't come from anything, so that's just empty set. That's fine. The pre-image of xy, so xy, that came from AB, well, that's fine, that's in T. But the pre-image of this YZW, so if I look at YZW, this came from CD, and if you recall, CD was not in T. That set CD was not in T. There was T here. AB's there, but there's no CD. So CD is not in T, so G is not continuous. We found that the pre-image of this subset, this open set, was equal to this one, and this is not an open set in here because it's not in the topology. Okay, so that's roughly how it works there. So another example here, if we take the set x0, 1, 2, we take the set of all subsets of x. So T now is everything. It's the empty set, it's the set x itself, it's a set containing 0, set containing 1, set containing 2, all the pairs 0, 1, 0, 2, 1, 2. So it's got all of the subsets there. And if I take any, so this is topological space, if I take any function mapping fxt to itself, then f is automatically continuous. Any function at all mapping this topological space to itself is automatically continuous because every subset of x is open. So the inverse image of any subset of x has to lie somewhere in here, because it's got all of them, will lie in T, and so will be an open set. So this is an extreme example here where you can take any function at all defined on this topological space mapping to itself, and it will always be continuous. The inverse image of any of these must be one of these, and hence inverse image of open is open. Well, next we're going to consider what happens when we take the composition of two continuous functions. Can we combine two continuous functions together? And the answer is yes. And so here's our theorem, our third and final theorem in fact. So we take xt, ys and zu are three topological spaces. We have f maps xt into ys. We're going to say if that's a continuous function, and g maps ys into zu as a continuous function. Then the composite function g circle f mapping xt into zu is also continuous. Now it's nice to draw a little picture here of this. So there are the three topological spaces. I'll just draw them as big circles. So this one here is the topological space xt. This is the topological space ys. This is the topological space zu. So f maps from there to there, and g maps from there to there. And the composite function, which is g circle f, goes from here to here. This is called g circle f. Notice the order, because when you apply this, you'll have to firstly apply f to send me to there, and then apply g to send me to there. So we write this as g circle f. And that if that function's continuous and that function's continuous, then the composition of these two is also continuous. Now just note that for any set A, the pre-image of g circle f is the pre-image of g firstly, and then you take the pre-image under f of that result. You may have seen that in earlier courses, perhaps in set theory, but this is the inverse of the composition is the composition of the inverses but backwards, and that works the same for pre-image. Okay, so what do? We have to take an open set A in the last space. So there's the set A. It's an element of U, and therefore it's an open set. Now, since G is continuous, I can take the pre-image of this back over here, and I'll call that set B, and that has to lie in S, because G is continuous, so the inverse image of open is open, and here open means belongs to the topology. Now I do the same thing using F. Since F is continuous, I can take the pre-image of this open set back here, call this one C. I can take the pre-image of this set back here, and F is continuous, this is open, so inverse image of open is open. So this set C is also open. And finally then, if we now take G circle F of C, we're going to end up with A, and that means the inverse image of, so I should have written, perhaps write this here, so I have written it here, sorry. So G circle F inverse of A, that is, we're going to take this set A and go back to here. By definition, this is F inverse G inverse of A. G inverse of A gets me to B, so this is F inverse of B, and F inverse of B is C, which is open. So the inverse image of open is open, and that means then that G circle F is continuous. Okay, final little section here is on what are called homeomorphisms, and these are really trying to find a way of checking whether two topological spaces are essentially, well, the same. Homeomorphic means they have the same shape. So two topological spaces xt and ys are said to be homeomorphic, literally having the same shape, if there is a function f which has an inverse, now this is an inverse now, a fair dinkum inverse, such that both f and its inverse are continuous. So you want a continuous function that takes you from here to here and back again. And the two spaces are said to be homeomorphic. And this is really leading us, well, we're not going to go any further with it, but this really leads into one of the other branches of topology, which is looking at what shapes are essentially the same, that one can be deformed continuously into another one. Anyway, so on the real line, the open interval x is minus 1, 1 on the real line, and the real line itself are homeomorphic. So let me just squeeze in down here the picture of this. So what we're doing is we're looking at, we're going to take the function inverse tan a half pi x. Now if we draw that, we'll get this. So it's got an asymptote here. You might like to get your computer to draw it if you're not sure about this one, but it looks like this. This function is invertible. If we look at open intervals on here, then inverse image of open is open, so this is continuous with the usual topology of open sets on the real line. And what it's essentially doing is it's mapping this interval, there's my x, across onto the whole of the real line. In other words, you can think of it like this. This interval, with the usual topology of open intervals in here being open sets, this topological space is homeomorphic to the whole of the real line. That is, you can take this and you can stretch it out into the whole of the real line. And topologically, we say these two objects, this interval and the whole of the real line, are essentially the same shape. They're homeomorphic. Because I have a function which is continuous, its inverse is continuous, and it maps one into the other. As a final example, the open disk x, y, and r squared, which looks like this. This is the open circle here, the open disk. This is also homeomorphic to this set, again with the usual topology of open subsets. So let me draw a picture of this one. So this is the inside of a disk, radius 3, and the open sets inside this disk will consist of all the open sets inside here. This thing here, this one here is an ellipse. So this is 3, this is 3, minus 3. This one here consists of an ellipse. If you put x to be 0, then you'll get y's between 2 and minus 2. So again, you can plot this one. And you put y as 0, x is in here. So here is this one. So that's this set here, consists of all the points in here. And this set here consists of all the points inside the circle. And there is a clear bijection between the two. So what am I going to do? I want it to go back from this set to this set. So I'm just going to leave x alone. And I'm going to replace the y here with 2y on 3. So if I put replace y with 2y on 3, when you square that, you'll get 4y squared on 9 times 9 quarters. That just gives you 1y squared. So if I replace this y with 2y on 3 and simplify, I'll get back to there. So there is and the other way around, if I want to go from here to here, I'm just going to replace y with 3 halves y. And if I square this, I'll get 9 quarters y squared, which is what I've got there. So there is a function, and here is its inverse. Looks like that. They're both continuous. They map open sets in here to open sets in here, and the other way around. And so these two topological spaces are what we call homeomorphic. They have essentially, from a topological point of view, the same shape. One is just a deformation of one shape into another by stretching. And these are examples of homeomorphic topological spaces. And that is the end of this recording, and in fact that's the end of the last lecture.